Section 2.3, day 2, part 1. What we're going to do is come in and take another look, or a more in-depth look, at those augmented matrices that have already been row reduced on the overdetermined and the underdetermined, to make sure you understand when it's a no solution, an infinite solution, and so forth. So on the board, I have the 4 examples that are on the handout from example 1. The directions say the given augmented matrix in row reduced form is equivalent to the augmented matrix from a system of linear equations. Determine whether the system has a solution and find the solution if it exists. So the first 2 examples, the number of equations and the number of variables are equal, and these are the ones we've already been looking at. And I know that because I see an X column, a Y column, a Z column, and the constant column in both example A and B. So what we're going to do is come in and take a look at the rows themselves. We'll notice that we do not have a row of zeros, so that means we have a single solution. We can see right off the bat that X is equal to 3, Y is equal to 1, and Z is equal to -4. And that's what we've been doing for the last several lectures. On B, what we're going to notice is this bottom row shows 0 on the left side, but a constant on the right side. So this is basically telling us that 0 is equal to 8, which is a false statement. And that means that there is no solution to that system of equations. The bottom 2 examples are the overdetermined and the underdetermined. So the first example, notice we have 3 rows, but only an X column and a Y column. So right off the bat, we know we're in trouble because something goofy is going on. I do have a row of zeros, but I'm going to backtrack up one and notice that I do have a solution for my X and a solution for my Y. So it is not an infinite solution because I have more rows, which means I have more equations than variables. I know what the variables are. I know that X is equal to 3 and Y is equal to 1. And this extra equation down here simply is something that is parallel, or the same equation as one of the other ones. So this equation that zeroed out in the row reducing matches one of the other equations. Okay, the last example though, we don't have a row of zeros. What we do see instead is an X column, a Y column, a Z column, and another column. So what your book does, instead of bringing in another variable, what they'll do is they'll call this an X1, an X2, an X3, and an X4 column, which is standard for matrices. What's our solution on this one? Well, we know we've got an X1 equal to 2. We also know that X sub 4 is equal to 4. So of our 4 variables, we know 2 of them. But the other 2 are sitting right here, and there's not enough information to give me a single solution. So this is when we go into the infinite solutions. And we're going to use a parameter. So since X sub 3 is further along, we're going to let that be our T. So then this equation becomes X sub 2 plus T is equal to a -1, or X sub 2 is equal to -1 minus T. So -1 minus T. So the solution to that last one, if we were to write it out, would be the 2 for X sub 1, X sub 2 is -1 minus T, X sub 3 is T, and X sub 4 is 4. So we do know 2 of the variables, but the other 2 are written in terms of the parameter. So let's do an actual physical example where an infinite solution or a no solution might crop up. Okay, so this is example 2 on the handout. It says the management of Hartman Rent-A-Car has allocated $1.512 million, $1,512,000 to purchase 60 new automobiles to add to the existing fleet of rental cars. The company will choose from compact, midsize, and full-size cars. They cost $18,000, $28,800, and $39,600 respectively. Find formulas giving the options available to the company and then give 2 specific options. So they want me to find formulas and then give 2 specific options that the company might use to purchase these cars. Let's come in and identify our variables. So X is going to be the number of compact cars, and those are costing, I just need the number, 18,000. Y is going to be the number of midsize, and those were 28,800. And then we have full-size cars, which are going to be a Z, the number of full-size cars, and that's 39,600. Okay, so in terms of the equation, we know all together we need 60 cars. So that would be X plus Y plus Z is equal to 60. And we know how much money we have. We know that each compact car costs 18,000. Each mid-size car is 28,800 times Y. And each full-size car was 39,600, and that's times Z. And that's going to be equal to 1,512,000, 1,512,000. And that's it. There is no other information in the problem to help me reduce down the number of possible solutions. I only have 2 equations and 3 variables. So we know right off the bat, it's an infinite solution. So we know, because the number of equations is less than the number of variables, that it's an infinite solution. So what we need to do is to come up with the parameter and solve the system. So we're going to go into our matrix. I have a 1, a 1, a 1, and the 60. When I go to write the next one in, I'm automatically going to divide everything by 100 to reduce some of the errors that could have come from those larger numbers. So I'm just going to cut off 2 zeros on every single one of those numbers and bring them in. So I have 180. I have 288. I have 396. And then we have 15120. So 15,120. And after row reducing what we can, we end up with this. So yes, I did some hand waving. This is where you need the practice to go solve these or reduce these. So once you've reduced it, you end up with 1, 0, -1, 0, 1, 2, then 20 and 40. So you notice that we went for the 1 on the diagonal again. We didn't bother with these guys over here because we don't have that 3rd row to get the 1 in that last column and the 0. So that's where you would stop with your row reducing. So what is that as a solution? Well, we know if we come in and let Z equal T, because that's the last letter that we have in our alphabet, then from the bottom row, we would have Y plus 2T is equal to 40. So Y is 40 minus 2T. From the top row, we would have that X minus T is equal to 20, or that X is equal to 20 plus T. So we now have a formula that'll tell me how many cars to buy if I come in and pick a value for T. So our formula would be 20 plus T, and that would be for the compact cars. We're going to use 40 minus 2T for the mid-size cars, and we're going to use T for the full-size cars. So there's our formula. What if we come in and let T equal 5? I am randomly picking that number. It has no meaning other than I just randomly picked it. So if T is equal to 5, then this would be the full size. Then the mid-size, which is, I guess we'll go back to the compact. So the compact cars would be 20 plus T, but T is 5. So that would be 25 of those. And the mid-size cars would be 40 minus 2 times our T, which is 5. So that's 10. So that would be 30. So if the fleet purchases 5 full-size, they will also need to buy 25 compact and 30 mid-size to hit their total of 60 and they're 1,512,000. So there's one possible solution. The directions actually ask for two. So let's come in and let t equal some other number. Let's let t equal 10 and see what happens. So if we buy 10 full-size cars, then what else do we need? So the compact cars would be 20 plus 10, which would be 30 of those. And the mid-size cars would be 40 minus 2 times 10, which is also 20. So sure enough, 20, 30, and 10 is 60. And if you add the price tags on them, you'll end up at that same 1,512,000. So we found a formula, and then we gave two specific options. So you can base how much you want on how many full size you need.